The regard of relativity. Well, hello again, my fantastic physicists. I always say life is like riding a bicycle. To keep your balance, you must keep moving. And for moving objects, everything becomes relative. Which leads me on to one of my finest stories, called On the Electrodynamics of Moving Bodies. Have you met Hans and Eduard? They're twins, you know, off on a great space adventure to help us explore the complexities of space and time. Eduard is an astronaut, and he's getting ready to zoom to our nearest star system, Alpha Centauri, while Flight Director Hans will remain on planet Earth to direct his brother Eduard on his mission. Say goodbye, boys. We have a rocket to launch. Hans needs to prep mission control for the pre-launch sequence. Mission control look like they're ready. So many buttons. And look, here's Eduard heading towards the rocket. Oh, the excitement of a rocket ride. Quick, let's help Eduard up to his flight deck and explore the relationship between gravity and time. Can you see the button? The longer you hold it down, the more charge you will give it, and the further the lift will travel upwards. Be careful not to charge beyond the green bar. Are you ready? Go! Remember to repeat until Eduard reaches his rocket. Do it again. When lower, time appears to run slower to us. You can do it! As the lift falls to Earth, time ticks slower. You're too close to Earth. Time's running slowly. When lower, the pendulum slows down. Lower, slower. Time runs slower on Earth. When lower, the pendulum slows down. What is happening to the clock? Look at the pendulum. It's ticking faster. You can do it! The clock is showing the effect of gravitational time dilation. Look at the pendulum. You did it! Eduard is now inside the Einstein selfie rocket. Activate main engine. Ready for launch in T-10, and onboard computers have full control. 7, 6. Main engine activated. 3, 2, 1. And liftoff! Einstein's selfie rocket is on its way to Alpha Centauri. Safe journey, Eduard. Bon voyage! Wow, what a blast! So much energy. Gravity didn't stand a chance. Alpha Centauri is quite a distance from Earth. We'll have to speed up a lot to get there in time. Can you see the distance to Alpha Centauri at the top? We need to get Eduard there. Move the spaceship by swiping on this area quickly and repeatedly. You'll have to go as fast as you can, but be careful not to break the laws of physics by reaching the maximum speed of light. Ready to swipe? Give the rocket more velocity. The closer to the speed... No! We've reached a singularity. Time doesn't exist now. Ah! Do you want to watch the rocket shrink? Increase your velocity. Nothing can break the laws of physics. Slow down. and make time travel faster. The faster the rocket travels, the shorter the rocket appears. Speed of light? Nothing. It's too late. The clock has stopped ticking altogether. Ah! Speed up the rocket more to witness length contraction. Keep swiping at the bar to keep the rocket at this speed. You're at just the right velocity. Well done. We all know light obeys a speed limit. Faster speeds mean time passes slower. What you see before your very eyes is length contraction. Faster than light particles just do not exist. The faster the rocket travels, the shorter the rocket appears. Watch your speed! Watch out! Time has slowed down a lot. This is dangerous. Way to go! Outstanding! Nothing can break the laws of physics. Slow down and make time travel faster. Length contraction is happening right before your eyes. Nearly hitting the target speed. We all know light obeys a speed limit. Well done! We finally made it safely to Alpha Centauri. It's a solar system made up of 3 stars. How cool is that? It makes our solar system look a bit boring by comparison. Eduard wants to capture this special moment. It's selfie time. Say cheesecake, or as Mama used to say, Käsekuchen. Let's head back to Earth and see how Hans has been getting on down in mission control. Eduard is so excited to show him his new selfie. Relativity is how different people see the same thing in different ways, depending on their frame of reference. For example, an elephant is so big compared to an ant, but is so small compared to planet Earth. In exactly the same way, my theory of relativity says that for Eduard, time appears to run differently depending on where he is and the speed he is traveling in relation to Hans and planet Earth. The consequences of my theory of special relativity become very obvious only when you travel at very high speeds. I discovered this when I was 26 years old. Remember when Eduard was in the lift? The higher he went, the faster the clock was ticking. This effect is called gravitational time dilation, and it's happening because the Earth is so big it curves the fabric of space-time and slows down time. And it's why clocks on satellites high above the Earth run faster than clocks down on Earth. I proved this to be true in my theory of general relativity, which took me 10 years of hard work. Do you remember when the rocket was zooming through space at great speeds? The clock went slower the faster the rocket went. So the rule is faster rocket, slower clock. This phenomenon is called velocity time dilation, and it's what makes time travel theoretically possible. Remember how the rocket got squished and squashed when speeding up? It shrank. This phenomenon is called length contraction. So not only time is relative, but length is also relative. So our new improved rule is faster rocket, shorter rocket, and slower clock. Great human heroes before me proved that the speed of light remains the same for all people and is not relative to how fast they move when they measure it. So because the speed of light cannot change, time and length need to squash and stretch to compensate. Simple. All I needed to work this out was some imagination, a lot of hard work, and ginormous doses of synaptogenesis. It followed from the special theory of relativity that mass and energy are both but different manifestations
of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be
converted into a very large amount of energy, and vice versa. The mass and energy were, in fact, equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932, experimentally. Oh my! Time really does fly when you're having fun. Hold on a second. Is that Hans? Why does he look different? Is he going to a fancy dress party? Actually, no. Remember what we've learned about the relativity of time. Eduard's time, while in the fast-moving rocket, has run slower in comparison to Hans' time back on Earth. As a result, Eduard has aged far less, and for poor old, very old, Hans, he aged at a faster rate compared to Eduard, and is now a very old granddad. I know that my story sounds incredible, but we have very strong evidence that my theory of relativity is true. But remember to never stop questioning.